Hi, my name is Margaret Strong, and I am SU Robotics team lead. This year, we are very excited to unveil our rover, Odin. SU Robotics is a multidisciplinary team comprised of students from various disciplines of engineering and sciences. Our team is made up of 5 sub-teams: the mechanical team, programming team, electrical team, science team, and business team.
Odin's frame consists of a welded aluminum chassis with an upper roll cage to protect critical electronic components, such as the batteries and drive controls. A large central payload bay allows multiple experiments and hardware packages to be mounted simultaneously. In order to stay within the size restrictions, we've constructed a spring-loaded locking mechanism for the antenna, allowing it to fold and lock into both horizontal and vertical positions. Our rover suspension system features a custom-manufactured double wishbone design utilizing an adjustable pneumatic shock. This allows us to modify the ride height of the rover for various tasks. The angled suspension arms allow the tires and wheels to get ahead of the nose of the rover in order to clear obstacles before they can hit the frame. Odin uses a wide wheelbase, occupying the 1.2 meter limit, and a low center of mass in order to increase stability on uneven terrain. Our drivetrain consists of 4 DC motors, utilizing a planetary gearbox in order to produce 52 foot-pounds of torque to clear smaller obstacles as well as summit steeper hill climbs. 30-centimeter low-pressure air tires are used in conjunction with a 3D printed clamshell hub in order to maintain ground contact. Our arm features 6 degrees of freedom, which allows it to manipulate both large and small objects with precision positioning and minimal backlash. The arm utilizes 2 heavy-duty linear actuators capable of withstanding intense payloads. The end effector features worm gears in order to passively maintain positions while holding dynamic loads. We've built subassembly modules from laser-cut acrylic paneling to house our computer banks.
At the low level, we establish a communications link with the rover via Ubiquiti Networks radio equipment. This provides us with a transparent Ethernet bridge, which allows us to use modern network protocols to communicate and manage the rover. At a high level, the base station communicates with services running on the rover via gRPC. Every core module on the rover is exposed via a gRPC service, and these services may call on one another as appropriate. For instance, the autonomy service will pull data from the sensor service and the computer vision service, and issue commands in autonomous mode to the command and control service. These modules are deployed on Raspberry Pi Model 4s, and in the case of computer vision, it is instead deployed on an NVIDIA AGX Xavier to maximize the efficiency of our computer vision. By using gRPC, the rover systems are more modular than a monolithic API-style application, and this modularity allows us to easily redeploy individual services to different onboard computers should the need arise, such as in the instance of a partial hardware failure. Both the arm and the end effector are implemented with closed-loop motion, allowing for precision control of the 6 degrees of freedom allowed by the arm and end effector assembly. Autonomy is achieved through a combination of sensors and computer vision. The rover uses a GPS and an IMU to establish its relative position within the field, and uses that to guide autonomous navigation. Additionally, a high-resolution camera is used to scan for and detect the AR tags that mark the waypoints, the gates, and the endpoints of the mission, applying a computer vision algorithm running on the AGX Xavier. Once the AR tags are detected, the rover will move towards these detected tags, providing the path is not obstructed.
Our electrical system is powered by 2 independent lithium iron phosphate batteries, one dedicated to the drive systems and the other dedicated to the processing and communication systems, enabling us to isolate our core critical components. For the drive system, we are using 60 amp passively cooled speed controllers with quadrature feedback, and for the arm, we are using specialized closed-loop controllers that have integrated PID loops, allowing for seamless integration and low processing expense. Most of the electrical subsystems are designed to be completely modular, using several mounting panels and interconnects. We have also designed custom printed circuit boards to assist with the rover's science experiments.
The science team will be implementing 3 distinct methods of soil analysis to determine the presence of current or passive life. 2 of the methods include chemical analysis and search for ATP and organic compounds. The organic composition of the samples will be found via paper strip tests, and the colorimetric result will be analyzed through cameras. A non-intrusive method will be applied to soil and rock samples to determine mineral composition. Grain size, grain distribution, and potential fossils will be analyzed using high magnification microscopy. Mineral assay is a reliable test for its independence of soil collection mechanism and for its retrieval of informative data. Lastly, the soil collection mechanism involves gravity feeding of the soil into the filtering station. The rover currently employs a prototype that will be replaced by a linear actuator.